So a set is closed under a given operation if the result of applying the operation always produces another element within that set. And that key word always there is important. Every combination using our operation produces another element in the set. If the set is closed under the operation, in notation we can write AB is an element of S, so we stick our hand in the set, we pull out an A, and we stick our hand in the set and we pull out a B, and then we use our operation. Our operation could be plus, multiply, divide, subtract, whatever you like, and the idea is that every single choice of A, every single choice of B, when we apply the operation, produces something inside of the set. Let's try our idea of being closed in this following example. So let's suppose we start with a set: happy, unhappy, and surprised. And we're going to combine these items in our set with the operation meets. So we have a happy meeting an unhappy, a happy meeting a surprised, and so on. So the table below defines what it means for each of our objects to meet one of our other objects. So the result of happy first meeting an unhappy would be a surprised result. And our question is this set that we've made up closed under the operation meets? So what we'd have to do to make sure that this set is closed is to check every single possibility. Check all of these possibilities. Looking within the table, did we ever go outside of our original set? Our original set was happy, unhappy, and surprised. Everything that I just circled is all within the original set. So this particular operation is closed under our set. So let's write down this answer. The whole table is in our set S. Therefore, S is closed under the operation meets. So we'll write under meets. So now we'll discuss an example. But before we do that, let's make sure we really understand this word always. Always within the set. When we apply the operation, we always want to land within the set. We don't want that 1 divided by 0 problem bringing us outside of the realm of numbers. And something that's not defined within our set is no good. So, when the result of applying the operation is sometimes, or maybe possibly never at all, within the set, our set is not closed. So mathematicians are very, absolute about this concept of a law. The closure law is one example of a law, and we need it to be every single case of being back in the set in order to qualify the law as being true and the operation being closed. If it happens just one time that we apply our operation and it brings us outside of the set, then we say it's not closed. And now every law in mathematics is like this. If there's a rule, we want it to be always true. If there's exceptions, then we don't really say it as a law. Maybe we have to explicitly state those exceptions and look at things case by case. So to show that a law is true, we need to provide a reason why it's always true. We need some kind of what mathematicians call a proof. That's simply an explanation that tells you and convinces you why the law is true. And often you might need some kind of variable to represent a random example. to show that every single example fits the law. To show that a law is not true, however, you just need to pull out one counterexample. If you can find one single counterexample, then you'll know that you can't always show it's true because you found that counterexample. Let's put this to test in an example below. So let's explain why the set of even positive integers is closed for some operations and it's not closed for some other operations. So let's consider this set of 2, 4, 6, 8. We have positive even integers. Notice that it's written in both list notation and builder notation. So in the builder notation, we're allowed to take any positive integer, the natural numbers, and plug the natural numbers into 2 multiplied by your natural number, always giving you either one of 2, 4, 6, 8, 10, on and on and on and on. So if we were to try to explain why this was closed, we would need to show that every single example, when we add or when we multiply, gives us a result that is one of the positive even integers. So we can just try some examples like 2 plus 2. Well, that will give me 4. And you could try something else like 2 plus 4. That would give me 6. Or you could try 4 plus 10. Now, 10 is not listed in this part above, but it still is one of the numbers because it fits that pattern. So you get 14. Okay, we can see that we seem to be getting more positive even integers. 20 plus 22 would give us 42. Now, we can't keep going on and on and on. There's no way that we could test all of these possibilities. There's actually an infinite amount of positive even integers. It would be hopeless to test all the possibilities. Now, you might say, well, it doesn't seem like I can come up with anything weird that will bring me outside of the positive even integers that we're coming up with here. But maybe your friend has come up with this weird example, and it does bring you outside of the set. You don't know until you write down some kind of convincing reason why it's always the case. So these examples, well, they kind of lead us to the direction of saying, yeah, this thing is probably closed. It's not quite convincing. So in order to be convincing that we have a set that is closed under this operation, we really need to use a variable. So I don't want to have that scrap work as my final answer. I want to particularly take a random a that is in my set of even integers, even positive integers, and a random b, and work with the a and the b. Now, to be a little bit more descriptive about the a and the b that I've just pulled out of this set, I can actually say that it's 2 times a positive integer, or 2 times a positive integer. That just gives me a little bit more of a description of what type of number I've found inside of my set. So what we want to know is if we take 2a plus 2b, can we convince ourselves that we get another positive even integer, no matter what the a is and no matter what the b is? Now, if you factor out the 2, here's the trick, you get 2a plus b. Now we can be convinced that this result that we just came up with here is something within our set. How can we be convinced of that? Well, this right here, a plus b, is a positive integer. So positive integer, or a natural number. Then when we take that natural number and we multiply by 2, we guarantee that it's even. So we can convince ourselves that, yes, this is an element of our set, capital E. And it doesn't matter what the a and b is, we always end up in that set. Let's try the same thing for multiplication. If we take 2a and multiply it by 2b, we can write our result out as 2 multiplied by 2ab. Just as above, what we have is a positive integer represented in the brackets. When we take that positive integer and we multiply it by 2, we can guarantee that we have an even positive integer. So it works out in all cases to explain why E, the capital E set, is closed under addition and multiplication. Okay, now let's try something different. Let's find counterexamples to show that E is not closed under subtraction and division. So if we take two numbers from this set and we subtract, is it possible to get outside of the set? So let's just take, for example, 6 minus 2. If we take 6 minus 2, we get 4. Now, 4 is an element of capital E, but this does not mean that our set is closed. This is just one example. We can keep searching for other examples, and if we do 2 minus 6, for example, what we get is negative 4. Negative 4 is not an element of capital E. So what we found is a counterexample that brings us outside of the set. So let's take this original stuff, erase that out. That didn't really help us towards the answer. It was an unsuccessful counterexample originally with the 6 minus 2. So now let's try dealing with division. So we'll try to find a counterexample that shows that if you divide two numbers within our set, it's possible to get outside of the set. And again, you might fail to come up with a correct counterexample by trying something like 8 divided by 2. 8 divided by 2 is 4, and that's inside of our set. But if you do 2 divided by 8, you get 1/4. Our set didn't have any fractions. So this is not an even positive integer. It is certainly outside of our set. So here's a proof versus counterexample where in one case we showed that we're always within our set when we use addition and multiplication, but it's possible to come outside of the set with subtraction and division.